Oncology clinics operate under a relentless ticking clock. In each room, physicians make rapid, high-stakes decisions based on complex, shifting data. One critical decision is triaging patients with metastatic renal cell carcinoma, or MRCC. When determining whether a patient should receive dual immunotherapy or a combination of an immune checkpoint inhibitor and a targeted kinase inhibitor, the path forward hinges entirely on accurate risk stratification. But extracting that risk profile is labor-intensive. Manually cross-referencing lab values against complex clinical guidelines costs time and introduces a margin for human error. To solve this bottleneck, software developers are translating validated prognostic models into instant, automated point-of-care digital tools. In the era of advanced, highly targeted immunotherapies, relying on manual calculations for critical triage pathways has become an obsolete administrative bottleneck. This infographic outlines the IMDC, or Heng criteria, the definitive prognostic algorithm for MRCC. It predicts survival by evaluating a 6-factor matrix, assigning 1 point per risk factor. 2 clinical variables check if Karnofsky performance status is under 80% and if time from diagnosis to treatment is less than 1 year. 4 laboratory variables track abnormal thresholds for hemoglobin, calcium, platelets, and neutrophils. A score of 0 is favorable risk, with a 43.2-month median survival. 1 or 2 points means intermediate risk, and 22.5 months. 3 or more indicates poor risk, dropping survival to 7.8 months. The IMDC risk score acts as a definitive clinical gateway. It provides the empirical justification required to deploy specific, high-cost combination therapies in the modern standard of care. This reliance on precise prognostic scoring extends far beyond solid tumors. Complex stratification algorithms dictate treatment pathways across the entire spectrum of oncology. In hematology, diffuse large B-cell lymphoma, or DLBCL, presents a similar triage challenge, where accurate survival prediction directly dictates the clinical strategy. Instead of the IMDC criteria, DLBCL relies on its own specific framework, the International Prognostic Index, or IPI. A comprehensive digital tool must support multiple panels. Here, the interface accommodates the classic IPI alongside the enhanced NCCN IPI. Because frameworks differ, a score of 2 on classic and 3 on NCCN both translate to low intermediate risk. Because these algorithms are ubiquitous, clinicians require a unified, instantly accessible platform to manage them, rather than relying on a fragmented collection of standalone web calculators. The OncoToolkit interface was engineered specifically to eliminate the administrative friction of calculating these models by hand. It translates the 6 IMDC criteria into a vertical series of rapid binary inputs. By requiring the clinician to simply toggle yes or no against the exact clinical cutoffs, rather than typing in raw lab values, the interface prevents calculation errors at the point of care. This streamlined data entry takes seconds during a live patient encounter and generates the patient's risk tier output instantly. In clinical tools, user interface design is about prioritizing zero-friction data entry. If the tool is cumbersome, it will simply not be used at the bedside. A frequent point of failure in modern medical technology is the black box algorithm, software that issues a clinical recommendation without showing its work. Translating rigorously validated prognostic models into usable software requires absolute evidentiary transparency. To achieve this, the tool includes a clinical context panel to validate the output. It lists the primary source evidence, tying the calculation to Dr. Heng's peer-reviewed paper, and exposes the exact mathematical logic, the sum of 6 risk factors at 1 point each. Software earns clinical trust only when it refuses to obscure its logic. It must expose its underlying mathematical and evidentiary framework directly to the physician. Beyond immediate bedside triage, this data serves a broader purpose, fueling retrospective academic research. Every isolated risk calculation performed in the clinic holds massive statistical value, provided it can be securely and efficiently aggregated. The software acts as a direct bridge to the research lab. A simple export function allows clinicians to extract all calculated patient profiles instantly. Once exported, a built-in CSV polisher acts as a necessary intermediary step, taking those disorganized raw inputs, handling any missing values, and harmonizing them into a uniform dataset. By separating this clean export pipeline from clunky, restrictive electronic medical record systems, the ecosystem removes the traditional technical barriers to clinical data aggregation. The final destination for that polished CSV data is an automated, browser-based statistical environment. This interface evaluates treatment efficacy, allowing physicians to run complex statistics without coding. It automatically generates outputs like chi-square analysis, log-rank statistics, and subgroup hazard ratios. The ultimate output is publication-ready Kaplan-Meier curves, displaying survival probability over time and hazard ratios for direct download. This continuous, frictionless workflow, from a bedside IMDC calculation to an automated survival analysis, represents the ideal life cycle of modern oncology research.